Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on solving quadratic equations using the square root method and completing the square. So I'm going to work through 12 different examples of how to solve a quadratic using the completing the square, and we're going to work through problems where the a is not 1 as well as when the a is equal to 1. Now, before I get into the step-by-step kind of method for solving using completing the square, I just want to do a quick little review of what is the difference of completed square? What exactly is that process? Well, each of these problems that I have selected are in what we call standard form. There we go. I don't know why that was like slowing down. And what we're going to do to use the square root method or in complete is we need to go ahead and put them in vertex form. So we're going to complete the square. So we're going to rewrite them in this form. Now, the vertex form is also very useful as far as identifying the transformations and the vertex, but that's not what we're doing here. Right now, we're going to be focused on solving using completing the square. Now, solving a quadratic using completing the square is not really necessary. Typically, we always want to solve a quadratic, the easiest method would be factoring as long as you know how to factor. And even if you didn't know how to factor, typically most students would prefer to use the quadratic formula, but that is again if you remember the quadratic formula. So the completing the square is a very useful process for converting from standard form and to vertex form. And in this video, we're going to actually work on using completing the square to solve our quadratic. So I'm not going to look at the other two methods, factoring and quadratic formula. I am just going to solve all of these examples by completing the square. Now, before I go and get started, because I don't want to do the long version of completing the square, or at least the explanation. What I'm going to do is I'm going to explain this process by understanding what all of these quadratics have in common. So if you look at all these quadratics, you see that yes, they're all quadratics. They're all, have an x squared, and they're all trinomials. Now, what's important about these is what they all have in common is they're what we call perfect square trinomials, right? Notice that the first term is squared and the last term is squared numbers as well. So what that means is each and every one of these can be factored into what we call binomial squared. This is x plus 1 times x plus 1, which is x plus 1 squared. This one is x minus 1 times x minus 1, which is x minus 1 squared. And if you thought I was doing a pattern, you are absolutely correct because that is the pattern. So this one would be x plus 3 times x plus 3, so x plus 3 squared. This one's x minus 3 times x minus 3, that's x minus 3 squared. And therefore, you can kind of see like that pattern continues. Now, obviously, we could continue doing that pattern with different numbers, but there's important things here that I want you to recognize about perfect square trinomials. One, the last and first term have to be squared numbers, and then the middle term is basically going to be 2 times whatever this is going to be 2 times whatever the square root of that last number is. And if that number is positive, then my factored form would be positive. If that middle term is negative, then my middle term would be negative. All right. So that's what we're going to do. We're going to want to create these. And what I want you to understand is if you have a perfect square trinomial as a standard form, you can then just factor it to put it into vertex form. But most often than not, it doesn't work that easily. Like for instance here, this is not a perfect square trinomial. So what we're going to do though is we are going to say, well, if I have n squared plus 2n, what number would I need to add to that to make it a perfect square trinomial? And you'd say the answer is 1. So what I'm going to do is I'm going to put that in parentheses and add 1 to it. Now, again, we just can't randomly add 1, right, to a problem. If we're going to add 1, then we have to make sure we subtract 1, right? Think about an equation. If you have an equation that's, like equal on both sides, if you add something, then you're also going to want to subtract that as well to like keep it still balanced. So if I have a negative 15 and a negative 1 here, I can just leave those on the side. Now again, here is going to be our perfect square trinomial. So that would be n plus 1 quantity squared. This becomes a negative 16 equals 0. Well, now what you notice is I have an expression where I only have one variable. So now I can solve using what we call the square root method. So I can add a 16 to the other side. Then I have n plus 1 quantity squared equals 16. Now, before I can subtract the 1 to isolate the n, I'm going to take the square roots of both sides. And therefore, I'll have n plus 1. Now, remember, when we introduce the square root, we have to use plus or minus 4. And then I'll subtract the 1. And so therefore, let's move my work over here. So I have n equals plus or minus 4 minus 1. So again, we have to make sure now we solve for both of them, right? So 4 minus 1 is 3, and I'm going to use a solution set. And negative 4 minus 1 is a negative 5. So you can see there are our two solutions, and we know that hopefully you recall from a quadratic, we should have our two solutions. All right, so that was the slow worked out way, and obviously you also could have factored that, would have been the faster way, but I wanted you guys to kind of see how the answer worked. So let's just try to kind of speed it up again. I knew to solve this, I had to get that constant to the other side. So why don't the first thing I do is just get the 6 to the other side and complete the square here. So if I put the 6 to the other side, what number should I add? Like, well, let's do it this way. So if I add a 6 to both sides, now let's look at it this way. If I have x squared plus 10x equals 6, what number should I add to this to make it a perfect square trinomial? Well, again, you can see that number is 25. Now, here's another way to look at it. Rather than adding and subtracting on the same side, which kind of gets people confused, you could also just add 25 to both sides. Right? So you could add and subtract, add and subtract on one side, or you could just add on both sides. That's still going to remain that balance. So again, I added this 25 that created that perfect square trinomial, which is x plus 5 quantity squared, and that equals 31. So a little bit less step that I have to do here. Now I can just introduce the square root. Now again, notice I can't take the square root of 31 like I take the square root of 16. So I'm just going to leave that as x equals plus or minus the square root of 31. Oops, I'm sorry. That is going to be x plus 5, right? Equals plus or minus, and then we'll subtract the 5 on both sides. So therefore, my solution set here, we can just write as negative 5 plus or minus the square root of 31. All right, so there you can kind of see, hopefully you can kind of get the idea of what we're doing now. So now I'm just going to kind of work a little bit quicker. So obviously we can get through this whole lesson here. So I'll put the 15 to the other side and then actually, let me explain one other way to do this because I'll let you reference this as well. I can do these now in my head, at least for this worksheet. It's very simple, but sometimes you're not going to get something that's up here, right? Sometimes you're going to get a 12, or a 16 or a 7 or a 3, something that is going to be a little bit more difficult. So you can always find the value, which we can always find this number, which we call that completes the square by taking b divided by 2 and squaring it. And again, just watch. 2 divided by 2 is 1. 1 squared is 1. 10 divided by 2 is 5. 5 squared is 25. So if we take the middle term divided by 2 and square it, that's always going to give us the value that's going to complete the square, which is very helpful when we have problems that are not very easy to create a perfect square trinomial. But all of the problems that I have selected on this worksheet can be found over here. So that's why I like to use this method from there, but I'm going to kind of work through my head now and go from that, or go use my head, but kind of explain through problems. So in this case, I'll do a 6p. Let's see, that's going to be a plus 9 equals, I'll put the 15 to the other side and then add 9 to the other side. This is now p plus 3 quantity squared equals 24. I'll introduce the square root here. Now this square root can be simplified. Let's see, that's going to be what, 6 times 4, right? So plus or minus the square root of 4 times 6. Now again, we could take the square root of 4, which is going to be 2, and then we can minus the 3. So p equals, let's do a negative 3 plus or minus 2 square root of 6, right? So you can take the square root of 4, that gets it outside of the radical, and we'll just leave it like that. We don't need to put it into our solution set. We can just leave it from there. Next example, I'm going to do the same thing. I'll subtract the 18 to the other side, and I'll complete the square. So this is going to be a 4b plus 4. Equals a negative 18 plus 4. This is a b plus 2 quantity squared equals a negative 14. Now, when I take the square root here, I have a little issue, right? So typically, if you're studying quadratics at this moment, then you have at least talked about the complex number system. So therefore, our ability, we can go ahead and use I. So hopefully, at least if you're watching this video, that's something that you've gone through, because I will use the answer instead of saying like no solution, which is something we might do in like algebra 1. I will talk about the complex number using the imaginary unit I. So therefore I have b plus 2 equals plus or minus I square root of 14. I can't simplify that. So therefore I'll just subtract the 2 here, and b equals a negative 2 plus or minus I square root of 14. The next one, let's see, I have x squared minus 10x. Let's see, that's going to be plus 25 equals 23 plus 25. So I'm adding the 23 and I'm adding the 25 on both sides. This becomes an x minus 5 quantity squared equals what, a 48. Now I know that 48 can be simplified. 16 goes into there 3 times. So therefore I have x minus 5 equals plus or minus, let's see, square root, that's going to be 16 times 3. So that'd be plus or minus 4 times radical 3. And therefore x equals, add the 5 to the other side. And again, all I did was I broke up square root of 48, just like I did here. I just didn't show my work. You can rewrite that as 16 times 3. And the square root of 16 is 4. That's why that 4 came out. I'm just trying to be efficient with my answers now. Once I've already kind of explained things once, I'll just kind of move ahead a little bit. All right, for the next problem, I'm going to subtract the 4, complete the square here. So this will be x squared minus 8x. That's going to be... Actually, we didn't do this one? Oh, I forgot to do this one. X squared plus 8x. Let's see, that's going to be plus 16, which would be x plus 4 quantity squared. And then an x squared minus 8x plus 16 would be an x minus 4 quantity squared. Okay, so we have an x squared minus 8x. Let's see, that's going to be plus 16 equals a 4 plus another 16. Okay, let's see, that's going to give me 20, which I can again simplify. This can be factored down into an x minus 4 quantity squared equals 20. Now I'm going to introduce the square root of both sides. So I get an x minus 4 equals square root of 20 can be broken down into the square root of, I'll just do this one, 4 times 5. So that can be reduced to 2 times 5. Add the 4 to the other side. So x equals 4 plus or minus 2 square root of 5. Okay, so those are the easy ones. Now let's get into the ones that are a little bit more difficult here. So the problem with our completing the square that we have previously done is all of these have a coefficient of 1. Okay, so we can only complete this, or we can only find that perfect square trinomial when we have a quadratic that has a coefficient of 1. So if we look at the second example, if you recognize what I did was I only completed the square for my quadratic and my linear term. For the constant, I just got that over to the other side. Well, that's kind of like the same thing we want to do here. Like, first thing we're going to want to do is add a 9 to the other side, and I'm going to want to factor out the 3. Because again, we can't complete the square with that coefficient there. So I'm going to factor out the 3, and then I'll have a v squared plus 2v equals 9. Now I can go ahead and complete the square inside my parentheses. And by doing this, I get, I add 1, then I have to add 1 over there, right? Okay. Now we have to be very careful though, because you actually didn't add a 1. You added a 1 that's being multiplied by 3, right? Because if you take that 3 you factored out. Well, you could always distribute that 3 back, right? So you're actually not adding a 1. You're adding a 1 times 3. So when I add a 1 over here, I need to multiply that by 3 as well. So now I can factor this down. This becomes a v plus 1 quantity squared plus 3. 9 plus 3 is going to be 12. And now we're just going to solve. So before I take the square root, though, I need to divide out the 3. And I hate doing this, but I ran out of space, so I'll continue over here. And then here I have v plus 1 quantity squared equals 4. Now I can introduce the square root. V plus 1 equals plus or minus 2. Subtract 1, subtract 1. Let's use a solution set here. So 1 minus 2, or 2 minus 1 is 1. Negative 2 minus 1 is a negative 3. Okay, now let's do it again. So I'll put the constant to the other side, right? So I'm going to subtract a 14. And then I'm going to factor out a 5. So therefore I have a p squared plus 2p equals negative 14. If I was to complete the square here, I would need to add a 1. So it would be 5 times p squared plus 2p plus 1 equals a negative 14 plus 1. But again, that 1 is being multiplied by 5, so this one needs to be multiplied by 5. So now I have 5 times p plus 1, quantity squared, equals, let's see, that's going to be a negative 9. Now again, I realize that even when I divide out a 5, I'm still going to have a negative value here, right? So this one's going to be nice and messy, but that's cool. So I can't take the square root of a negative number. I'm still going to do it. So I'm just going to write my, my my complex number with that fraction there, or with the square roots. But I'm just going to leave it as that, unless, obviously you needed to like simplify this. It kind of depends. But just remember that's going to be a plus or minus. And let's see, that's going to be the, that'd be square root of square root of 9, or negative 9 is going to be a 3i over the square root of 5. And then we could subtract the 1. So p equals a negative 1 plus or minus. Hopefully, and let's just leave it like that. 3i over the square root of 5. Maybe you could rationalize the denominator if you needed to, but let's just kind of leave it as that. All right, so the next two is factoring out a 4 first, and then adding the constant over. So if I factor out a 4, I'm left with an n squared plus 2n equal to 5. Again, let's complete the square here. So we're going to add a 1. And you can see, hopefully, guys, like the same pattern keeps on coming up over and over and over again. But then we're also going to add a 1 over here. But again, remember that's being multiplied by a 4. Here, that can be simplified to n plus 1 quantity squared equals 9. Divide by 4, divide by 4. Here I have n plus 1 quantity squared equals 9/4. So now I can go ahead and take the square root of both sides. So we'll bring that over here. And by taking the square root of both sides, I get n plus 1 equals 3/2. I'm sorry, plus or minus 3/2, right? Because you can take the square root of the numerator and take the square root of the denominator. You know what? I got time. Why don't we just show that? So then you can take the square root of both sides, and then you get n plus 1 equals plus or minus 3/2. Then I'll just subtract the 1. And in this case, rather than doing my fractions, you can leave it like that. You could add them to give you what? A negative 5/2, and then a negative or a positive 1/2. But I'll just leave it as the fractions for the sake of time. Wow, we're all subtracting out of 4 out of 8. That's kind of interesting, the problems we chose. These are all different, but then the last ones are all the same. So good, it'll be some good practice for us. So let's factor out the 4. N squared plus, oops, not plus, that's a negative. Say negative 2n equals 5, because I put the 5 to the other side. Complete the square here, that's good. Plus 1 equals a 5 plus 1 times 4. 4 times n minus 1, quantity squared, equals, again, 9. Just like the exact same problem it is, basically. Now we're just going to be subtracting a 1. So actually, I'm just going to go through the same process. That would be 1 plus or minus 3/2. All right, let's do this one. So I factor out the 4, so therefore that's going to be k squared plus 2k equals a negative 22. Again, I kind of am used to plus 2k plus 1, and then equals, let's see, that's going to be a negative 22 plus 1 times 4. Well, that's going to give me a negative 18, so I now know I'm going to be using my complex numbers. So factor that down, because we've already done that like multiple times. And this gives me a negative 18. Now I'll divide by 4. Oh, actually, that makes it a little bit better. I forgot about the dividing by 4. So that's going to make that reduces to a negative 9/2. So I have a k plus 1 quantity squared equals a negative 9/2. Now I can introduce the square root. So therefore I have a k plus 1 quantity squared equals, let's see, you can break up the radical to the numerator and denominator. So the square root of negative 9 is negative 3. And then we'll just leave that 2. I'm sorry, let's put that as an I. You can put the negative in anywhere. It doesn't really matter. I'll just write it from there. And again, that is going to be a, not a negative, that's a plus or minus. Okay, but again, taking the square root of a negative number, that's where the I, that's our imaginary units. But again, when you introduce a square root, you have the positive and the negative. So therefore, k equals -1 plus or minus 3i over the square root of 2. And again, you can maybe simplify that by rationalizing the denominator. All right, last one here is, again, really same thing here. We're going to factor out a 4. X squared plus 2x equals -7. Again, going to complete the square. So x squared plus 2x plus 1 equals a -7 plus 1 times 4. In this case, we add that. That's just going to give us a -3. So that one's not as bad. Let's see. That's a quantity 1 squared. That's a -3. Divide by 4. X plus 1 quantity squared equals a -3/4. Now, when I introduce my square root over here, let's see, it's going to give me an x plus 1 equals, again, we're going to do plus or minus. We're going to have I square root of 3 over 2. So I can take this, so when I take the square root of -3, that's going to be I square root of 3, and the square root of 4 is just going to be 2. And then we just need to put the 1 to the other side. So that's going to be equal to -1 plus or minus I square root of 3 over 2. And there you go, ladies and gentlemen. That is the process for completing the square. I think once you get pretty good at it, and you start recognizing a lot of these patterns, you realize that you might actually decide to use completing the square over factoring or the quadratic formula. And especially, it's always helpful if you cannot factor it or you cannot remember the quadratic formula. Sometimes completing the square is going to be your best friend. There you go, ladies and gentlemen. Hope you enjoyed. I'll see you on the next video. Cheers.